For this video, I'm going to review work, energy, and power, and I'm going to go over the very basic concepts and ideas from this unit. There was a lot going on in this unit, but this will just go over the basics, so you might want to go over your notes as well. All right, so energy. Energy is the ability to do work. So if you lift something or if you move something across the floor, that ability to do that, that's energy. Work is a change in energy. So work and energy are very much related. So work could be lifting a box. It could be pushing it to the side. It could also be changing energy into something else. So you could change electric energy into mechanical energy, and that would be doing work. So work can convert energy into other forms. Now, work and energy are both measured in joules. And a joule is a kilogram times meters squared divided by seconds squared. Or you could say it's this. Okay, so you could solve for work by multiplying the force by the distance that you apply that force. So let's say that you are pushing a box. You have a box that you apply a 10 Newton force over 5 meters. So you push a box with a force of 10 newtons over a distance of 5 meters. So you could just simply multiply 10 by 5 to get the work done. This would tell you that you had 50 joules of work. Now, when you're looking at work in this respect, so when you're looking at the force and the distance has to be parallel to the force. So if you're looking at the work done to move that box up a ramp, and really the goal is to have this box at the top of this ramp, and maybe it's on a 1 meter tall surface. The distance that you're really going to be concerned with here is going to be the 1 meter tall. And you're only going to be looking at the force in that direction and the distance in that direction. So the force and the distance have to be in the same direction. So if there's no distance, no work is done. So basically, if I hold Splat the cat at a 1 meter height and I'm just holding him there, no work is being done on the cat because the cat didn't move if I'm just holding the cat there. So for work, when we're looking at this formula right here, you need to remember that the distance is going to be in the same direction as the force, and if there is no distance, there's no work done. Okay, so we have two different types of forces when it comes to this stuff. We have non-conservative forces and conservative forces. A non-conservative force is a force that does not conserve energy. So basically, if you push a box across a floor and there's friction, that friction is going to ensure that some of the energy that you have used to move the box is converted into another form, like heat. So that's a non-conservative force. A conservative force does conserve energy, like gravity. So if I'm lifting a box and I'm just doing work against gravity, my energy will be completely conserved. None of that energy will be converted into something else unusable like heat. So all the work done in this kind of situation is conserved. All energy is conserved. So a good example is an example with a ramp. So if you have a box and you're comparing the work done maybe like at a 30-degree angle, a 60-degree angle, and then just straight lifting the box. And the box is going to the same height. So if we're neglecting friction here, So we are just simply lifting the box, and then we're also pushing it up these two ramps. But if we neglect friction, all the work done against gravity will be the same. Okay, and that's because gravity is a conservative force, and since it's a conservative force, the pathway taken does not matter. So if you have a question where it's saying, well, how much are asking you to compare the work done, in this case, moving a box up a 30 degree incline, a 60-degree incline, and just moving it straight up, and it all goes to the same height, technically the same work has been done. The work against gravity is done in all three situations is the same. All right, so mechanical energy. Mechanical energy, you need to remember, is just kinetic energy plus potential energy. So kinetic energy involves movement. So if the object is not moving, there is no kinetic energy. And then potential energy can be a couple different things. Potential energy could be chemical energy. It could be the energy conserved in a spring, or elastic potential energy. It could also be gravitational potential energy. All of those things are types of potential energy. So it could be gravitational potential energy, which is the energy that we usually look at, or it could technically be chemical energy. Gravitational potential energy has to deal with height, and you can get the gravitational potential energy by multiplying the mass times little g times the height or the distance it is from the ground or some reference point. It has to be with respect to a reference point. So maybe you have a table that's 1 meter tall. So it's above the ground by 1 meter, and then you lift something off this table an additional 1 meter. So your height has to be in respect to some reference point. So if it's in respect to the table, it would be 1 meter off the table. If it was with respect to the ground, it would be 2 meters off the ground. So you have to consider the reference point when you're looking at GPE. All right, so what is the GPE of Splat the cat if he is lifted 10 meters off the ground? Okay, so if he's lifted 10 meters off the ground, you know his mass is 1. The height is going to be 10 meters here. And then little g, of course, is 9.8. So to solve for GPE, just plug it in. So 1 multiplied by 10 multiplied by 9.8. So when I get this, my GPE should be 98. And that's going to be joules. So the cat has a potential energy of 98 joules. So really, the cat has potential to do 98 joules worth of work by moving. All right, so energy is conserved, just like momentum, but really it is total energy that is conserved. So energy can be converted into a lot of different forms, like heat. So total energy is always, 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 always conserved, but other types of energy are not always. So like mechanical energy. Mechanical energy is potential and kinetic. Well, if there is a non-conservative force, like friction, some of that mechanical energy will be converted into heat. And that is not a type of mechanical energy. So if you have energy before an event, that energy should be equal to the energy afterwards. So we can use that information to find, let's say, the velocity of something as it moves. We could also use it to find the height that it started at. So we can use this equation to find we could use it to find the height that the object initially was at, the height that it ends up at, and the initial velocity and final velocity of the object. Also, we can use it for the mass too. Okay, so Splat the Cat is dropped from a 10-meter tall building. What is his velocity right before he goes splat? What is his kinetic energy? So again, let's write out our information, and we're also going to do a before and after table here. So the event is Splat the Cat falling. So before he fell, his mass was 1 kilogram. He was at a height of 10 meters. I also know little g. And I also know that his initial velocity was 0 because he was dropped. So afterwards, I know his mass is still 1 kilogram. I know that his height should be 0. I also know little g still. And I'm looking for his velocity at this point. So when I have my equation, my potential energy initially plus my kinetic energy initially is equal to all the energy afterwards. And what I want to do is I want to see if anything crosses out, if anything equals 0. Okay, so my initial potential energy. Well, I definitely will have initial potential energy because he's being held at a height. So nothing here equals 0. My mass is 1, little g is 9.8, and my height is 10. For my kinetic energy, well, he has a mass, but his velocity is 0 here, so I can cancel that out. So afterwards, well, he has mass, he has little g, but his height is now 0, so I can take that out. And then I know that he will be moving right before he hits the ground, so I can't take that out. So really, it's this is equal to this. So let's go ahead and plug everything in. My mass is 1, little g is 9.8. My height is 10. That's equal to 1/2 multiplied by my mass of 1 multiplied by v squared. Okay, so 1 times 9.8 times 10 should give me 98. Okay, 1/2 times 1 will just give me 1/2 v squared. Okay, so I will divide out the 1/2. So I get 196 is equal to v squared. And then don't forget to take the square root at the end. So my velocity here is 14 meters per second. And if you had read this question, you might have realized that you could have also used kinematics here, which is perfectly acceptable. But there is another way to solve this. All right, so if I want to know his kinetic energy, well, I simply need to go back and plug it into the kinetic energy formula, which is 1/2 mv squared. So my kinetic energy is equal to 1/2 multiplied by my mass of 1 multiplied by 14 squared. So 1/2 times 14 squared. 14 squared would give me 196. So my kinetic energy should just be 98 joules. Oh, okay. So one more thing before we go. Power. Power is the rate that work is done. So it's the rate that energy is changed, or it's the rate that you're lifting something. So it has to deal with time. So really, power can be equal to 3 different things here. And of course, there is one other thing, but that deals with electricity. So power is equal to the work divided by the time. Or you could say the change in energy. So if you know the object's kinetic energy, and it started from 0, like maybe his velocity was 0 at first, if you know the change in energy, you can also solve for the power. You don't necessarily need to get the work or the force and distance here. Now, power is also equal to force times velocity. Now, if the velocity is constant. Now, power is measured in joules per second or watts. Now, the other equation that involves power is electric power, which is power is equal to current times voltage.